In this video, we're going to talk about a very commonly used and very powerful way of sorting numbers using a technique called merge sort. Merge sort is one of those sorts that belong to the divide and conquer family. As you know, divide and conquer is a very old technique, and what it implies is to take a problem and subdivide it into smaller problems with the idea that the smaller problem, because it has a smaller size, it would be easier to solve. Once we solve the little problems, we can put them together and find a solution for the original problem. So a merge sort is a divide and conquer sort in the sense that in order to sort values, which we're going to assume are contained in an array, we're going to divide the array in halves and keep repeating the process until we get to have subarrays exactly of length 1. So we start with one big array and we end up with a bunch of little arrays. That's the division part. Then we're going to take those little arrays, which have exactly size 1, one value in each of them, and we're going to merge them. And then we'll end up with arrays of length 2, then arrays of length 4, followed by arrays of length 8. They're going to be powers of 2. When I go through the example, you're going to see exactly what I mean. So as usual, we're going to start with a series of random values, and I'm going to use numerical values because they're easy, but this technique can be applied with integers or doubles or string objects or any object of your choice. So the first step is going to be to partition the array in exactly 2 halves. And conveniently, I started with 8 numbers. So if I'm going to divide them into 2 halves, I end up with 2 arrays, each of exactly length 4. What would happen if the numbers are not even but odd? Then one array will have 4 elements and the other array will have 3 elements. Or one array will have 100 elements and the other array will have 99 elements. So it doesn't really matter that we're dividing them in exactly half. We're partitioning them into 2 groups. And one group could be larger than the other. So once I do this, then my second step is to take each of those halves and again partition each half into 2 subarrays. So now I'm going to end up with 4 subarrays. And here are my 4 subarrays. Notice that at this point, all I'm finding is the middle of the array and then copying values into the new arrays. None of the values are swapped. They are not exchanging positions. They are not being compared either. I just find the middle of the array and then simply divide that into halves if possible, and then just copy the values. In real life, if I have thousands of elements, I will keep doing this until I hit a point where all my subarrays are exactly of length 1. So if you look at my example, my next step here will be to divide each of these subarrays that have currently length 2 into subarrays of length 1. And that's exactly what I have. So what you see here is a collection of 8 very small arrays. 8 arrays, each of them of length 1, each of them with exactly 1 value. At this point, I have finished with the divide part or aspect of this algorithm. And now what I need to do is my last step, which is to merge these subarrays in order. And again, it's going to take several steps, several iterations, probably done recursively, but I'm going to be doing that until all the values are merged. But when I merge them, I'm going to merge them in order. Let's go through that. My first step in my process, remember we are here, I have 8 small arrays, so I'm going to merge the first 2 into an array of length 2. And when I'm talk about these 2 values, I'm going to merge them in order. So the result is a subarray that has 2 values, 14 and 29, which happens to be in order. Next step, the next 2 values, and again merge them into an array that has length 2 and copy the values in order. So that gives me 13 and 37. And then I'm going to merge 40 and 25, and that's going to give me 25 and 40. And finally, the last 2 numbers are 32 and 64, and that gives me the last array of length 2 with those 2 values. Next step, merge these 2 subarrays into a subarray of length 4. And that's exactly what I have done here. And I have, again, inserted the values in order. And then I'm going to take the next 2 subarrays, which are these 2, and I'm going to merge them into an array of length 4 where all the 4 values are going to be in increasing order. So notice, and again try to visualize this with arrays of 100 elements. So I'm going to have an array, let's say, of 100 elements where the 100 elements are in order. So here I only have 4 values, they are in order, 4 values, they are in order. And now the last step is going to be to merge these 2 subarrays, and I'm going to merge it into one. And as I merge them, I'm going to merge them in order. So the end result is one array that has all their values in increasing order, which is what I want to do. But something that is very important to understand is to be clear on how the algorithm for merge sort works and why it sorts the numbers faster than other techniques. So let's go back to the previous step, the one where we have 2 halves. We have this half on the left, this half on the right, and we need to merge these 8 values into a single array. Now assume that each of these halves has about 20, 30,000 elements which are sorted in increasing order, and then we need to merge these 2 halves, so the final array is going to have 50,000 elements. Of course, for demonstration purposes, I only have 8 numbers, but you should understand how the technique works. So what happens? Well, the technique, the algorithm is going to compare the first value on one half with the first value of the other half. Decides which one is the smaller and place that into the first position. So comparing 13 and 25, 13 is the smallest of the 2, and it's going to place it in the first position. Then the algorithm, because we're using arrays and indexes, will realize that it needs to compare now the second element of this half with still the first element of this half. So it always picks 2 values to compare. In this case, it's going to compare 14 and 25. And obviously, the smaller of the 2 is 14, so it's going to insert 14 in the right position. The algorithm will continue now comparing the third element in this half with still the first element in this second half. And at this point, when it compares 29 with 25, it recognizes that 25 is smaller, and then it puts 25 in the correct position. The algorithm, again, is comparing 2 values at a time, one from each half, and then placing them in order in the final array. Let's continue a little bit more. So at this point, the algorithm will compare 29 with 32 and decide that the smallest of the 2 is 29, and then it's going to compare 37 with 32, and the smallest of those is 32. The next step will be to compare 37 with 40, and the smallest of those 2 is 37, so inserts 37. So again, it has been comparing 2 values, one from each half, and inserting the smallest in the correct position. What happens at this point? At this point, the algorithm recognizes that there are no values left on this half. All these 4 values, 13, 14, 29, and 37, have been inserted in the correct places in the final array. And because there is only one half and nothing else to compare with, then the algorithm realizes that, and what it does is to simply copy the values that are left in the array. So in this array, we have 2 values left, 40 and 64. Those values cannot be compared with anything else. They're simply our copy. Let's go back to the previous issue. What if you have, let's say, 5,000 elements left, and only you have one half? So you have 5,000 elements which cannot be compared with any other values. Those 5,000 elements are going to be simply copied. And therefore, we save time because we are not comparing 2 values. We're simply copying from one subarray into the final array. That's where the power of merge sorts resides. One of the things to notice, and I'll discuss that in a minute in the analysis, is that there were no swaps. In other words, when I start dividing, these 2 numbers belong to the first array. I'm not swapping their positions. I'm not comparing those values. When I try to divide these 2 subarrays, again, there are no comparisons. Simply, I'm splitting them into 2s, and one more time, I'm splitting them into halves until I have arrays or subarrays of length 1. Okay, so there is no comparisons at this point, and there are no swaps. Now, when I start merging them in order, of course, I have to compare. So I'm going to take these 2 subarrays, and I compare the first one of one subarray with the first element of the another subarray, decide which one is smaller, and put that on the first position. When I get to this point, I'm going to do the same thing. I'm going to take the first value of one subarray, compare it to the first value of the other subarray, decide which one is the smallest, and insert that into the first position. So merging the subarrays does require comparisons, but again, there are no swaps. That's what makes this technique very, very fast. So let's do some more formal analysis. Of course, if you were to take a look at the algorithm, it's going to be a recursive algorithm. What we're doing is repeating the same process, divide by 2, divide by 2, divide by 2, until we get subarrays that have exactly one element. And then merge 2 at a time, merge 2 at a time, merge 2 at a time, and eventually we get to merge 2 halves, and when you merge 2 halves, you have the whole array. As I just pointed out, there are no swaps at all. What we do is to split arrays by half and then merge them using comparisons. But very important, there are no swaps, there are comparisons. So the algorithm analysis is as follows. Let me assume that we have n numbers of elements, and for convenience, let me assume that these numbers of elements is going to be a multiple of 2. It's going to be 2 to the power of something, which I call k. So I'm going to have an even number of values. That's perfectly okay. If you say, well, what would happen when n is an odd number? The analysis applies, but for simplicity, we're going to assume that the numbers of elements is not only even, but that is a power of 2. So if we analyze 2 to the k, then k represents the level of recursion, meaning how many times we're going to apply the recursive code that says we need to split by 2. And every time that we apply a recursive code that says you need to split by 2, there has to be later on a corresponding recursive code that says you need to merge this. So if I split 4 times, then I'm going to have to merge 4 times. If the numbers of splits is 1,000, the numbers of merges is going to be 1,000. So going back to this formula here, if the numbers of elements is some value which is 2 to the power of k, what is the value of k and what does it represent? Well, k represents the numbers of partitions, how many times I'm going to divide by 2. And the value of k is simply log base 2 of n. We had seen this in other algorithms, for example, in binary search and in binary trees when we divide by 2 and we get the same type of performance or efficiency. Now, how many times do I have to divide by 2? Well, that depends on n. So I'm going to say that is O n. So now I need to say, okay, how many times do I need to divide by 2 and make a simple multiplication? And this is going to be then n log base 2 of n. So the efficiency, the expected, remember expected means average running time of the merge sort is n log base 2 of n. So this is actually faster than any sort which is n square, and it works very, very nicely. Now there is a disadvantage, an inconvenience, a limitation of merge sort. Because we are dividing our original array into half, because we are splitting into many subarrays, then we're going to need memory to create the divisions, to create the smaller subarrays. And then we need to merge them. So the process of partitioning the original array into half and the process of merging those partitions into the original array requires extra memory. Other than that, there are no other negative or inconvenient aspect of the merge sort.